students can get feedback. And I find that this is a very helpful piece too, and I wish I could find more ways to use it. Sometimes I skimp on that part a little bit. Tonight what we're going to do is we're going to look at the challenge area, explain buffer systems, and we're going to see how it would integrate into a chemistry lab investigation. The one that's been targeted is number 15. I'm going to talk a little bit about how I integrate it into investigation number 16, bringing that those AP Insight materials together with the lab, and then we'll have an open discussion also at the end. So here's this challenge area, explain buffer systems. And I think that, again, most of us know that the entire curriculum is not covered in AP Insight Chemistry, but what they have done is identified the toughest areas to understand and provided us the resources to get through these really tough areas of our curriculum. And I would hope that you all agree that explaining buffer systems is can be one of those sticky areas for us to teach. The other nice thing about this whole process is that they give us so many formative assessments so that we can quiz the students on small chunks and larger chunks to see how they're doing before we would assess them for a grade in our classrooms. So I guess the question we can have here is, where can this challenge area be found in our curriculum framework? I think that this topic was chosen mainly because most of us probably are working with equilibrium right now in our classrooms. And if we are not already teaching buffers, we're within a week or two of maybe having this as part of our conversation in our classroom. And I wish I were there, Jeremy. I would love to say that buffers were behind me, but they're not in my classroom. They're ahead of me in about a week. And I think that one of the things that we might want to talk about for a moment, if you're interested, is why are buffer systems so difficult to teach? What is so hard for the kids to learn when they try to explain and identify and actually manipulate buffer systems? And I'm just waiting to hear from you through the chat room. Yeah, I agree, though. You know, I find that I teach conjugate acid-base pairs both in first year chemistry and then consider it kind of a review coming into AP year for many of the students. But yet, even those, that simple concept of Bronsted-Lowry acid-base pairs is sometimes difficult. I always go back to looking at reactions when I teach buffers and bring back in how an equilibrium system can shift using Le Chatelet's principle. So on this slide, what you can see is that this challenge area is broken into three building blocks, and And those are, of course, how buffers work, design a buffer system, and protonation state. And Jeremy, I see what you've written about they struggle knowing when a buffer system is present. So I don't know how you guys handle it, but I do a day of titrations. I'm on an 80-minute block schedule, and I only see the kids 240 minutes per week. So what I do is I have them do make titration curves, perform these titrations for strong acid, strong base, weak acid, strong base, weak base, strong acid, and diprotic acids. I use malonic acid and maleic acid because I can get some pretty decent curves. And then we analyze all of that data. So every lab team of 2 students must perform a titration and get me a good titration curve. And then we share data within with around the entire class, this whole body of data, so that we can analyze these various situations and make sense out of them. And therefore, the building block that I used first, actually among this sequence, is I use protonation state, because of the first part of that performance task actually asks the students to explain a titration curve. And then from there, it asks them how an indicator works. So that fits in very nicely with my titration lab before I ever do a buffer lab. And I also spend time looking at hydrolysis so that the students understand how the salt of a weak acid or a weak base behaves in aqueous systems. And I find that it's just a qualitative lab I do, but it's helpful in laying this foundation that you're talking about, Maria, when you say that they have a trouble seeing how the conjugate actually behaves when it's in the salt form. So these building blocks are obviously important concepts for the kids to learn and be able to manipulate. And the order in which we present them must fit our roadmap, our personal roadmap, and that's why I've played around with this ordering myself. So this slide, of course, shows the recommended sequence of instruction. This is how it's shown, right? That how buffers work is building block A, design a buffer system is building block B, and then protonation state is building block C. And just to repeat myself one more time, I find that I can move protonation state up higher on the list and then hit the next 2. So let's look a little bit at lab investigation 15. And I don't know if you took time to download it before we began. Again, I use many times the Flynn version of the recommended laboratory investigations. And the reason I do is the timing. With an 80-minute block, I have a hard time using the labs that are in the College Board lab book that we all probably possess, and therefore I find that the Flynn version is more streamlined, and it works really well for me. The other thing that is true is I don't do investigation 15. That's the one that's entitled. It's entitled Buffers of Household Products, and so that you're titrating things like citric acid in the introductory exercise. And we know citric acid is triprotic, but when you titrate it, it really has almost a monoprotic looking titration curve. And then from there, the students are asked to devise a, 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 a procedure for doing a household product like Gatorade, for example, that is buffered by maybe a citric acid buffer or a phosphate buffer or both. And I find that sometimes those curves are just a little hard to analyze, and therefore many times the kids will miss the point. Yeah, I agree. That's why in my titration lab, I like to start with the basics and show some pretty classic titration curves. And Jeremy, do you get a nice titration curve with the vitamin C tablet when you titrate it? Yeah, because I tell you, malonic acid and malic acid or maleic acid, they really work very well, and they give you a pretty clean graph to analyze. Um, Right. So I dedicate an entire block, Maria, of 80 minutes. So I have the kids working in partnerships, just two kids, and then I just have standard burettes, and I put I have the kids put their sample in a 250 beaker with a stir bar on a stir plate, put that pH probe down in there, and then simply do an experiment where they can enter their volumes and it grabs that pH at that volume. All right. But I think we'll move on a little bit to talk a little bit about a buffer lab and see what we like to do. So before we get quite there, then here's a slide that talks a little bit about the difficulty for kids to make these connections. And again, there's a lot going on in the aqueous solution. So on that particulate level, can they visualize how this buffer is behaving? And how do they then relate that to what they may see on a titration curve? Certainly looking at the dominant species that are in the various regions of the titration curve, but especially in that buffer region. And Marie, I agree. It's the same thing I do. I give different assignments to every partnership, and then we all share the data so that we can get this larger collection in a shorter period of time. And I feel like I'm talking to the choir here a little bit, but I think because we're recording this to put on the website, I think it's important that I mention that within each challenge area, the teacher can unpack the challenge area under the Prepare tab and certainly get the background information they need to begin to structure how they will present this conversation about buffers to their students. And that is very helpful for the teacher that's very new to this curriculum. So just a few things that we should talk about here perhaps is that a lot of times my students, some of them are very capable math students, and so they're always looking to solve a problem rather than maybe understanding exactly what's going on visually at the particulate level, and also just the whole reasoning behind how how a buffer system works. And so I'm always having to take them back. And that's why I like some of the building blocks, because they have them work with visualizations. Some of them are just embedded in the questions, but on the performance task design a buffer, task 2 actually has the kids use what I call a tactile activity, where they will use either poker chips, or colorful poker chips, or paper clips, something they can manipulate, and they begin to look at what happens to the number of these manipulatives as they go through a chemical process. And it can be really helpful, I think, to some students to, just get that visualization with some tangible item in their hand. So I really suggest that you look at building block or performance task on design a buffer system, and look at task 2 because it's easy to set up for the teacher, and the kids can really begin to understand it. All right, well, I guess we'll move ahead. And I've got here on this slide a little excerpt from building block A on how buffers work. And I do this right before I go into my buffer lab. And what you can see is on this, this first task is that just looking at how to identify a buffer system. And then again, it's very structured. They're given a lot of information in a table, and then they're asked a set of sequential questions to discern the important aspects of this table. And then in this building block, task 2 will have them actually look at an unbuffered system versus a buffered system. And the buffered system that they use is they use just baking soda, sodium hydrogen carbonate, and they exhale their breath in it to set up a carbonic acid bicarbonate buffer, and then look at how it behaves when they add strong acid to it. So again, a simple first task, I believe, and then a second task where they're actually making observations. Then finally, task 3 gets to literally, I call it buffer math. The slide suggests that it's the quantitative explanation of how a buffer works. But whichever way you want to say, it's having to work some buffer problems. And I wish I could say that I let the kids work at their own pace, but I am always kind of watching the clock and monitoring minutes spent because I think at least task 1 and task 2 should be done in the classroom, and then maybe you could send task 3 home as homework and have the kids come back the next day, and then we would go over the task and make sure everybody's on the same page before we entered the lab on buffers. The other nice thing is, of course, you can give them that building block quiz of about 4 multiple choice questions to make sure that they feel okay about that section. And Jeremy's asked if I use the Henderson-Hasselbalch equation. I certainly show my students that equation, even though I feel like this new curriculum doesn't favor its use. And the reason I do that is that that's what a lot of chemists use. That's the down and dirty way of doing a buffer problem. But I also show them it's just an extension of using a regular approach of an equilibrium problem based on an equilibrium expression and using an ICE table to plug in. So I like to show them both ways, Jeremy. Right, Marie, I agree. I'm always going back to basics and then moving to sometimes what I call the shortcuts. So now notice that on the slide that's in front of you, it suggests that if after doing building block A, then proceed straight into building block B, designing a buffer system. Well, this is where I would change it up a little bit. My buffer lab that I use is a lab where the introductory activity has the students make an acetic acid acetate buffer, but it has them make actually 3 different buffers with a different ratio of acid to conjugate base. And then it compares those buffers to a straight pH 7 prepared buffer that I give them, and distilled water. And it has them add strong acid and strong base to these 5 different buffers: the 3 acetate buffers, distilled water, and then the pH 7 buffer. I really like this collection of data because it really, one, builds their lab skills, of course, but it also gives them the opportunity to see that certain buffers work better when there's additions of strong acid versus others work better with addition of strong base. And then we can look at those reactions and begin to understand why. So it introduces, one, making a buffer, but it also introduces buffering capacity. And like I say, it's the Flynn version of Investigation 16, and it's entitled Properties of Buffer Solutions. So that's the introductory activity. Now that takes a long time to do. So I give them data for the addition of strong acid, and then I ask them to get the data for the addition of strong base. And that way I can kind of cut a good 20 minutes or more out of that part of the laboratory, so that we then, during my 80-minute block, have time to talk about these results and begin to understand them. And then that sets them up for the second part of the experiment. And in the second part of the experiment, what the students have to do is I assign them a buffer to make that has a certain pH. They have to pick the conjugate acid-base pair that would be the best choice off of my supply cart of reagents. And then they have to prepare that buffer, check its pH to see if they actually hit the assigned pH given to them. And then they test the buffering capacity of the buffer they just made. And it's a really great lab, but I do it over a 2-day period on 2 different 80-minute blocks. And so what I like to do is I like to use performance task B, design a buffer system, is a review after I do my buffer lab. And it just really helps them, I think, kind of check that they understand what we just did in the laboratory. Yeah, I never thought about it that way, Maria, but sometimes, you can't just give, you can't have a wide open inquiry because it takes them forever to make a decision. So if there's only so many choices, then the decisions can come a little faster. Yeah, I really like this performance task B, design a buffer system to come after my buffer lab as a review. And then then I can use the little building block quiz for B as that final check before we move out of buffers. So let me move forward another slide here. So here's the suggestion that now the students would be ready for a buffer lab after doing both building block A and B. And like we just suggested, that perhaps building block A could precede the laboratory choice on buffers that you make. And then building block B might be a really nice review of what the lab just had them do. All right, so let me move forward again, because now here's where building block C could come in, yeah, and this idea of predicting the protonation state using pH and pKa. But what's true is that if you look at task 1 in this building block C, it's really having you examine the buffer region of a titration curve. So that's why I like to take this this performance task and move it as a follow-up to my titration lab that precedes my buffer lab. And you can see that task 1 would be covered very nicely then. It would be very helpful as the students have completed collecting the data to make a titration curve to analyze it in this way. Notice that the other piece is task 2 has them look at how an indicator works. Now, I do how an indicator works back when I first am talking about Le Chatelet's principle, and I use it as one of my chemical systems to explain how shifts of an equilibrium occur due to a concentration change. So I've already done that lab a few weeks ago, so now I am able to come into this performance task and review how an indicator works. So I like that. I like that wrap around. I like that bringing topics back in again and again. Yeah. And I agree, Maria. Flynn does have a version of Le Chatelet's lab. I do Le Chatelet's as a demo lab. So I set up all of the systems on a little larger scale, and we observe them as a class and discuss them and analyze them. And one of my systems is usually using bromothiamyl blue as an indicator and looking at how it behaves as you add either strong acid or strong base, but look at it as an equilibrium system. And so the last part, task 3 of building block C, is um, applying what you know to new situations. So this example on this slide is showing, uh, you know, I guess this is a protein structure, right? Amino acid structure. And it's got 3 protons, A, B, and C, that are dissociable. And it asks in pretty much in what order would you expect the proton to be released. And I like this aspect of the performance task, because we know that often on the May exam, they will pull an example from biochemistry or environmental chemistry. And it's very important that the kids not be afraid of looking at these large organic structures. So it's such a powerful tool for us to be able to give them these kinds of questions to consider. And I keep saying it's just fundamental chemistry, you guys. So just use the fundamentals and you can tackle any one of these problems. And so I think we all agree that we know these are going to pop up. So isn't it nice if we can show them throughout our course these situations and make them feel comfortable with them? Yes, and I agree, Jeremy. Some like my text, Brown and LeMay, it's it's a it's I love it, and but it doesn't always give me these unique examples, especially laid out this way. I like how these are laid out. So let me move forward another slide, because this is hard for me to read the way I've got it. So let me just enlarge this a little bit so I can look at it. All right. So this is from this is from, oh dear, I've got my papers all jumbled up. Here I go. So this is from the Explain Buffer Systems Assessment, and this is the introduction to the teacher's guide that you see in front of you. And I think that, the point being that, this gives us this list of things that we've got to make sure we challenge the kids on. And it also, I like near the end here, it suggests that, we always have to keep reasoning out these questions using Bronsted and Lowry theory, Le Chatelet's principle, and equilibrium expressions. We're always going back to those fundamentals as we keep adding on more and more layers of understanding. And so that's a pretty crucial piece. So Maria's asked a question of both you and I, Jeremy, about whether Brown and LeMay does a very good job of dissecting the regions in a titration curve. And I feel it does all right. There are some particular graphics in it that I will point out to the students because I think that they are really instructional, and we'll spend time looking at those. Yeah, I agree. So, like I say, I'm not so sure it does a bang up job, but I do believe that there are certain, uh, what I recall is certain graphics that I like, illustrations or figures that I like, that I think are pretty instructional. And I bring those to the students' attention, and then we chat that up more. And so uh, here's a particular multiple choice type question on buffers. Take a look at this. Kind of ask yourself, what does a student need to know so that when they read this question, they can answer it with some confidence? And I think this goes right to Jeremy's last comment, that knowing the predominant species along the titration curve is very important. So, obviously a student, I think, has to have had some experience with that in order to challenge this multiple choice question. So do we all have our answer? Right. And I also think that if you just think about it, if you're adding strong base, then the fact is, what's that going to do with your conjugate pair? Well, it's going to neutralize more of your acetic acid molecules, and so therefore you're going to have a greater conversion to acetate ions. And just the common sense of it is you're dumping in strong base. If it's going to go one way, it's going to go up in pH. So something with maybe a little more rigor is this free response question. And again, let's say this would be a short free response. It just has parts A, B, and C. And indeed, you have to do some calculation here, but not anything that's too awful. But I always tell the kids, don't forget how to write an equilibrium expression, because often they ask for that. And what I find is after the students have worked a lot of equilibrium problems, they stop writing the expression and jump right into creating an ICE table and writing an algebraic expression to do the math. And so I continually have them practice this, and of course I also give them questions on my test in this kind of format, where part A is a pretty easy part, but please do it, get those points, and then move on and do the calculations for B and C. Indeed, but again, you can do it right from your equilibrium expression and knowing now the Ka value that you just figured out in B. So you could do it as a straight equilibrium problem and go right back to the basics. So we're at about 9 minutes till 8, and I thought we need to be hopefully at this part of our conversation. And so here are 3 questions that you may want to consider. For question 1, I think that, if we're just talking about this part in equilibrium, I do have the kids determine the Ka of a weak acid, but I do that experiment way back at the very beginning of my course. So when I'm teaching about chemical reactions in Chapter 4 of Brown and LeMay, it talks about acid-base reactions. Well, I start talking to the kids about weak acids and bases then. Focus on weak acids and have them actually do a Ka determination. And that kind of sets me up for now, where I am on these equilibrium chapters. In chapter 15, where it introduces chemical equilibrium, then I have them determine the Kc value for the formation of the iron 3 thiocyanate complex using a colorimeter. So I'm using visible spectroscopy. It's a simple little lab, doesn't take a whole lot of time. But again, it gets them using laboratory equipment in new ways. So we've already done a spectroscopy lab on crystal violet for kinetics. Now I'm going to use them for equilibrium. I do an experiment much earlier in the year on the percent of copper in brass and use a colorimeter to analyze the concentration of the copper 2+ as we react the copper with nitric acid. So, there's certain labs that I really enjoy doing that hopefully just build the kids' confidence in the laboratory setting. I see, Maria, that you do a titration, a redox titration of peroxide, and I actually do a titration of vitamin C with iodine, so it's a redox titration. And I like to show them how titrations are not just acid-base. I agree with you there. And Jeremy, I agree with you on question 2 that the power of AP Insight is simply that it targets these very, very tough places for kids to kind of get it. And it just polishes their ability to challenge themselves to achieving understanding through some very carefully structured performance tasks and formative assessments that I find absolutely invaluable. I wish that every AP chemistry classroom could have access to AP Insight. Let me ask you a question. Do any of you do a lab with on solubility product equilibrium? I have done them in the past, but I'm finding that in the last couple of years, because of the change of curriculum, I have no time to do a KSP lab. Yeah, Jeremy, that's exactly the procedure I use to do my Ka experiment in the very early part of the year, at the beginning of my school year. Because it's a very quick procedure. but the chemistry behind it is very important. So as I try to wrap this up, what questions do you have of me, if any? Yeah, I hear what you're saying, Jeremy, and I agree with that. See, all of my students, this is a second full year of chemistry coming in the door, and I've given them a summer assignment on the first 4 chapters of Brown and LeMay to challenge to see what they remember from that first year course. So we're up and running pretty strongly at the beginning of the year. Right. That's a lab I also do with iron thiocyanate, and you create the complex, and you can determine the equilibrium constant with the colorimeter. So just to bring your attention to this slide, I encourage you both to become active participants on our online community and discussion board. I was just chatting with a teacher today who's working on equilibrium, and so we had a little bit of back and forth conversation today. And you can create a thread, or you can participate in a discussion thread. And I look forward to both of you becoming more involved here as you find time to do so. I'm not sure, Maria, I understand your question, but I do think that we are definitely moving away from just solving problems through an algorithm. And I really think that, the more we can prepare the kids for using conceptual type learning and critical thinking skills, they're going to be a lot better off and much more successful, not only in May, but beyond. So again, I really do encourage you to share what works. It would be great if we could get more dialogue out there. I just feel like most of us are so stressed with time that, it's something we really think we should do and want to do, but sometimes don't get around to doing. Um, Maria, yeah, I see your question on STEM questions and the NGSS type questions, and maybe I just don't know how much response you'll get because I think really this is based on a lot of conversation on getting kids through that AP chemistry curriculum. So I'm going to move forward because instead of using this link on this slide, I'd like to direct your attention to the bottom of your screen. And I'd like you to notice that you can click on the link at the bottom of the screen, AP Insights Survey, and give us a little feedback of how helpful this hour has been. And I please encourage you to take the moment to do that. And I think probably we all know that we can contact the AP Insight folks at College Board pretty easily. I find when I email, they get back to me very quickly. There is a phone number on this slide, and you know that they have office hours on Mondays from 4 to 5 Eastern Standard Time, where you can actually phone in and talk to someone if you're having difficulty using the website or you just have some concern that you want to express. And so I'm going to stick around for another 5 minutes or so, and you can go ahead and log yourselves out if you wish. But I thank you for attending, and I thank you for the interesting conversation that we have. Yeah, Maria, I think that all you have to do is go down to the links down below and click on that. And I'm thinking that'll take you to the survey. At least that's what I was told. Very nice. I'm glad, Maria. We did a good job, you guys. It's only 8:03. And I wish you a good evening. Thanks, Jeremy. And thank you also, Audra. Well, we can keep this conversation going on our website. Yeah? We should talk about buffers out there for the benefit of many. Good night, Jeremy. And Audra, I'm not sure what I should send you an email about. Oh, okay, great. Yes, I will be glad to do that. I've got it. I think I'm getting a little tired this evening. So Maria, are you ready to sign off? Or do you have any other questions? Yeah, that's a good point. And it's finding the time, isn't it, to do all of this? Very nice, Maria. Thank you. And I think I'm ready to end this meeting now. Good night, everyone.